In this illustration, we'll analyze the friction and normal reaction acting on a falling rod. If we are given that a thin uniform rod AB is vertically placed as shown on a rough ground, and if its upper end is slightly tapped so that it starts falling due to friction and its lower end does not slip, we are required to find the normal reaction and friction at point B when rod is at an angle theta to vertical during its fall. Here you can see when the rod would be falling, and due to the work done by gravity, it will attain an angular speed which can be calculated by using work energy theorem. So if it is at an angle theta from the vertical, we can say its angular velocity is omega and angular acceleration is alpha, which we can simply calculate as we can write by work energy theorem. We use its center of mass has fallen by a distance L by 2 1 minus cos theta. Earlier it was at a height L by 2 and now the center is at a height L by 2 cos theta. So we can write it as mg L by 2 1 minus cos theta is equals to half I omega square, that is ml square by 3 multiplied by omega square. And this will give us the value of angular speed of rod, which is root of 3g by L multiplied by 1 minus cos theta. This is the angular speed with which rod would be rotating when it is at an angle theta. And we can also calculate the angular acceleration. Here we can write by Newton's law second, we use the net torque acting on the rod is due to its weight mg. So here we can write mg multiplied by the torque due to it is L by 2 cos theta, and this should be ml square by 3 multiplied by alpha. So torque is I alpha, which gives us the value of angular acceleration, that is 3g sine theta by 2L. Now we have got the value of omega and alpha. So these will give us the tangential and normal accelerations of the center of mass, as the tangential acceleration of center of mass would be normal to the rod and its normal acceleration would be towards point B, as it is in circular motion about center at point B. So here we can now write tangential acceleration of a rod center is this E tangential we can write as L by 2 alpha. So this value we are getting is 3 by 4g sine theta. And if we calculate the normal acceleration of a rod center, then this can be given as it is in circular motion at this instant, it is given by omega square r, that is omega square L by 2, and numerically this will give us 3g by 2 multiplied by 1 minus cos theta. We have taken the value of omega from this relation, and as we have got the value of E tangential and E normal, then we can write the equations of motion of rod. Then along vertical direction, here we can write mg minus normal reaction, as it will be experiencing n in upward direction and a friction toward right. So it is mg minus n is equals to m a y, and here acceleration in y direction we can write as this a normal cos theta plus a tangential sine theta. Here you can see if this angle is theta, here this will be theta, and from horizontal this angle is also theta for the motion of center of mass. And simplifying the values of an and at over here, you can calculate the final result which you'll be getting in this expression will be n is equals to this mg minus MAY, and when we substitute the values of MAY, this will give us 3 mg by 4 multiplied by 2 cos theta minus 3 cos square theta plus 1. That is the result of this problem. I'm leaving it for you as an exercise to substitute AT and AN over here and verify this result. And we can also write the equation of motion in horizontal direction. Also in horizontal direction, here we can see this equation we are writing in vertical direction. For horizontal direction, we can write the only force acting on rod is friction, which can be written as MAX, and acceleration of rod in x direction here can be given as A tangential cos theta minus A normal sin theta. Again, you can substitute AT and AN over here and verify the value of friction, which we'll get is 3 mg by 4 sin theta multiplied by 3 cos theta minus 2. That will be another result of this problem for friction acting on rod.